Hello everybody, I have another video today. We're going to be going over some basic motion on ramps, gravity, some really long word problems. It's going to be good. So to start out with this problem, we have a drone accelerating from rest up a straight ramp, inclined at 20 degrees above the horizontal. So I can already draw that. We've got 20 degrees above the horizontal. There's a drone, and it's going up this way. The acceleration along the ramp is 2 meters per second. So I can write that, 2.0 meters per second squared. And then I'm gonna underline it. What is the drone's vertical displacement when the horizontal displacement is 100 meters? So we have down here, horizontal displacement is 100 meters. So this is an interesting question because we have to first determine how much time it takes to move that 100 meters. From our kinematic equations, we have x of t equals x naught plus v naught t plus it's 1/2 at squared. In this case, it says I'm just going to set x naught over here to be 0. So this term goes to 0. And then it says it accelerates from rest, so v naught is also 0. So x of t is based purely on 1/2 at squared. Something really important to notice, though, is that the acceleration is not purely in the x or y direction. It's in it's 20 degrees up from horizontal. So we have to break it down into its different components. So we have acceleration in the x component and acceleration in the y component. In the x component, it is going to be, let's look at our triangle here. We have 2, here's our right angle. Here is 20 degrees, and the x component is going to be this bottom leg here. The y component is going to be the rightmost leg. So we have the x component is 2 cosine of 20 degrees. So 2 cosine 20 degrees, and then the y component would be 2 sine of 20 degrees. Right now, though, we're only worried about the x component because it was wondering the horizontal displacement. So x of t equals 1/2 acceleration, which is 2 cosine 20 t squared. And we know that the displacement, that's our x of t, is 100 meters. So that means 100 equals 1/2 2 cosine of 20 t squared. So we can rearrange this to find that, we multiply both sides by 2 to get rid of the 1/2. And then we will actually just go ahead and divide by 2 to get rid of this one. So both of those cancel. And then we'll divide by cosine of 20. So we end up with 100 over 2 cosine of 20. And then we need to square root this to get rid of the t squared, equals t. Let me plug that into the calculator real quick. So we would do 100 and then divided by 2 times cosine of 20, and then take the square root of that. And we end up with 7.29. And that would be seconds. Actually, I'm so sorry. I had a 2 here that wasn't supposed to be here. So it's actually just 100 divided by cosine of 20, which is 10.32 seconds. So this is our time, and we can now plug this into our equation for the displacement for y. So I'm going to erase this to make a little more space. So again, x of t equals There's no x naught, there's no v naught, so it's just 1/2 ay t squared. So our ay is 2 sine of 20. This 2 is going to cancel with this 2. And we end up with x of t equals just sine of 20 times time squared. And we can plug in our time value we found earlier. So x of 10.32 equals sine of 20 times 10.32 squared. And if you plug that into the calculator, this equals 36.43 meters as our y displacement. Okay, so now we have two students standing on a balcony 50 meters above the ground. One student drops a ball directly downward. The other student throws a ball horizontally at 10 meters per second. Determine which ball reaches the ground first and why. So this one doesn't actually have any math, but I'm going to draw a couple diagrams. So we've got our first ball, which is just accelerating downward. And then we have another ball, which has an acceleration downward, and then an initial velocity in this direction. It says horizontally, so it doesn't have any vertical component at 10 meters per second. Both balls are going to actually reach the ground at the same time. And the reason being because this velocity vector that goes 10 meters per second in the horizontal direction does not have any effect on the vertical velocity vector here. Neither of them, this one is dropping it. Our first student drops the ball. The other student throws the ball, but it's horizontal, and so it doesn't have any vertical component from the student initially acting on it. So if you were to use x of t equals x naught plus v naught t plus 1/2 at squared, you would need 1 for the x direction and 1 for the y direction. And the y direction has no additional components that the student imparts on it. In other words, this v naught, this 10 meters per second, only applies to x of the x direction for the ball. Okay, now I have a very intensive word problem. Go ahead and pause the video and read through this word problem to understand the situation that we're in. Okay, moving on, we have that we basically have some ascent data that we've recovered. That's what these two paragraphs explain. And we want to fill out this table and determine what exactly is going on. First thing we always do is we draw a diagram to describe the passage above. If you read the passage, I'm just going to go ahead and draw our diagram. Basically, we have our Stonewatch rescue team, which I'm just going to call SW. And then, they have some horizontal displacement and then some vertical displacement. And up here is Olympus. So they have some distance they need to travel here. And they have a total delta x that will need to travel, and then a total delta y that they will need to travel as well. So let's find delta x and delta y given our information. I'm going to fill out this, what this table is trying to tell us is that we have a lot of information about each segment of the journey. And it wants us to use the information we have to fill out the remaining pieces. So like this piece X here, it wants us to use the segments or the information from segment 2 to fill out that X. So this one I'm actually going to call x because it's the horizontal displacement during their 15-minute jog. So they have a velocity of 1.7 meters per second at an incline of 4.5 degrees. So I'm going to draw that. There's 4.5 degrees here, and then it's 1.7 meters per second here. And we know that they do this for a total of 15 minutes. So t equals 15 minutes. There's a couple different ways that you could solve this. You could find the vertical displacement and then use that. The way that I'm going to choose to solve it is by finding the x component of our velocity, which is 1.7 meters per second. So going back to our triangle, we have 1.7, and then this is 4.5 degrees. So the x component here is going to be 1.7 cosine of 4.5 degrees, not 45 degrees. That would give us a very different answer. So we now have our, I'm going to call this v sub x, so our velocity in the x direction. And we know that they travel for a duration of 15 minutes, and we assume no acceleration. It just gives us velocity, and so we assume they're traveling with a constant velocity, so there's no acceleration there. So the equation we would use for that is x of t equals x naught, which I'm just going to set to be 0, because we're just looking for displacement here, plus v naught t. So we have our v naught, that's our v sub x that we found. So this is 1.7 cosine of 4.5 degrees. And then we have our time t is 15 minutes. Now we need to convert that to seconds. There's 60 seconds in a minute, so 60 times 15 is going to be 900 seconds that they travel at that velocity in the x direction. So I'm going to go ahead and plug that into the calculator real quick. We get 900 times 1.7 times cosine of 4.5 degrees. And we get that they have a horizontal displacement for that section of their journey of 1,523.3 meters. I'm now going to use the exact same method we just used to determine this y value. It wants the vertical displacement of the third segment of their journey, where they're traveling with a velocity of 0.34 meters per second at a 55-degree incline. And they travel for 41 minutes. So let's draw our diagram. There is a 55-degree incline, 0.34 meters per second, and it wants the y here, which is going to be 0.34 sine of 55 degrees. Using the same equation from earlier, we're going to say y is equal to y naught, which we're going to set equal to 0. So we're just worried about displacement again, plus v naught t. V naught is the initial velocity, but since it's a constant velocity, we can just use our 0.34 sine of 55. And then our time t is 41 minutes. So 41 times 60 is 2,460 seconds. So I'm going to multiply that by 0.34 and then times sine of 55 will give us 685.1 meters that they travel in the y direction during that leg. So 685.1 meters. For this last segment, segment 4, we have to employ a slightly different method because we do not know time. So we do know the velocity, the direction of the velocity, and we know the distance traveled in the y direction, or our vertical displacement. So I'm going to draw a picture here. So we have 89 degrees at 0.05 meters per second. I now want since we already have the y component of displacement, I'm going to use that to solve for time. If you recall, the equation we've been using is y of t equals y naught plus v naught t. In this case, we have v naught. We again set y naught equal to 0. And instead of having time, this time we have our y of t. So we can use it to solve for time. Our y of t would just be 250 meters because that's the displacement in the y direction. So we still need v naught in the y direction. And this is just going to be y is equal to, I'm going to call it v naught y is equal to 0.05 sine, zoom in a little. Actually, just going to move this. There we go. So v naught y is equal to 0.05 times sine of 89 degrees. So let's go ahead and plug that into the calculator. 0.05 times sine of 89 degrees is 0.0499 meters per second, which makes a lot of sense because this is an 89-degree angle, and so we have very, very little velocity in the x direction here. Almost all of it is in the y direction. But we can still use this now to solve for y of t. So we have 250 to solve for time, 0.0499 times time. So we can rearrange this, divide 250 by 0.0499 to get our time as, let me plug it in, 250 divided by 0.0499 is 5,010.02 seconds. I'm going to ignore the 0.02. We would then divide that by 60 to get the amount of minutes that it would take, which is 83.5 minutes. So I'm going to go ahead and plug that in. That is a horrendously long stair. But they're climbing the stairs for 83.5 minutes. Pretty miserable experience there. Anyways, we now have our time. So I'm going to rearrange this equation again to solve for our x of t, our x displacement. It's going to equal x naught, which is 0, times v naught in the x direction, times time, which is our, multiply that by 60. It is 5,010 seconds. So we need our v naught in the x direction. That's going to be 0.05 times cosine of 89. So let me go ahead and plug that in. We get 0.05 times cosine of 89 degrees. It is a very, very small number. It is 0.00087. And then if we multiply that by 5,010, we get that they're traveling roughly 4.4 meters of horizontal displacement for that stair climb. So they're not really stairs, they're like straight up. Maybe that would make sense actually if the stairs are like this And they do that because then there isn't any overall vertical displacement. Okay, I'm gonna solve the last question of this problem now. Now you may have noticed that up here, I didn't actually fill out the velocity and the incline. I could, if you wanted to find the incline, you have your 2 kilometers of horizontal displacement and then your 350 meters of vertical. So you can use tangent to find this angle theta. And then you can use the duration that it takes to travel either of these distances to find your velocity. But it's not required for this problem. A lot of physics problems that you encounter, you can really get into it and you can determine a lot of things about the problem, but you don't need to. It wants us to determine the position of Olympus station using meters and XY coordinates. So going back to our diagram here, we need our delta X and our delta Y. That's going to be our meters and our XY coordinates. So I'm first going to do our vertical displacement. We have 350 meters plus 120 meters plus 685.1 meters and then plus 250 meters. Finally, we also have to add this 1850 meters that they start at. So plus 1850. So our Y is equal to 3,255.1 meters. For X, we have 2,000 meters plus 1523.3 meters plus 472 plus 4.4. So our X, we have 3,999.7 meters. So you could say in the position for Olympus station is going to be X, which is 399.7 meters, and then Y, which is 3255.1 meters. And that's it for that problem. Okay, for this next problem we've got that the EMS team has reached Olympus station and they now must signal Stonewatch, which was the base down below. We're still dealing with this same problem here. So, a couple important things. We have that they're going to use a flare to signal them. The flare exits the launcher at 110 meters per second. It must reach a horizontal distance of about 1,000 meters. And then it burns at peak brightness for only 12 seconds. And then it must follow a trajectory that maximizes its vertical motion. We've taken the liberty of writing down these known values and notes for things that we need. But if you're presented with a problem like this, you should 100% be writing down these known values and notes by yourself. So really, we just wrote down everything that I underlined. So finally, we want to draw a diagram, write some algebraic expressions for x of t and y of t, determine the ideal launch angle, and calculate the vertical position at t equals 12. So I'm first going to go ahead and draw a diagram again, but a little bit different. So down here, we have Stonewatch. And if you recall, this is at x equals 0 and y equals 1850. And then here is Olympus. And this is at x equals, I'm going to round, it was 3,999. I'm going to say it's x equals 4,000 and y equals 3255. And we know that the flare must reach a horizontal distance of 1,000 meters. We want the largest possible y direction. We want our launch angle, theta, as degrees from horizontal. And we know that it has a launch of 110 meters per second. So now I'm going to write some algebraic expressions for everything that's going on. So first, we want our x of t, our horizontal displacement. It's going to be 4,000 minus 110 cosine of theta times time. So this is just our x of t equals x naught plus v naught t. You may ask, well, why is there a minus sign there? You have to look at the diagram and realize that the vector is pointing to the left. Up to this point, we've assumed that to the right is the positive displacement. You can see that up here with these plus signs. And so if it's moving to the left, that is a negative displacement for x naught. And then I got this value of 110 cosine theta just from this. Here's our 110, here's theta, so our x displacement is 110 cosine theta. For our y displacement, we have our initial y, which is 3255. And then this is going to be plus, because it's moving in this same direction along this vector, which we've determined to be the positive direction for y. And then that'll be 110 sine of theta times time. There is, however, one more important thing that we need to consider for our y direction, and that is the component of gravity. As soon as it launches, there's going to be an a y component in the negative direction, which is 1/2 gt squared due to gravity. Okay, now we have the next part of the question is to determine the ideal launch angle. Remember, our important things is we want to maximize the vertical component of initial velocity while still maintaining horizontal range. So I'm going to first deal with our x coordinate. I'll remind you that we know that the visibility time is 12 seconds. So they'll launch it and it will immediately start burning at peak brightness, and then it has to remain visible for 12 seconds. So this means that x of 12, so that's our time, equals 4,000 minus 110 cosine of theta times 12. And we can use this to solve for our theta value, because we know that at 12 seconds, it's going to be at x equals 3002. That's this value right here. Sorry, I forgot that 0 there. But this is 4002 minus 1,000. This value is 3002 and then 1850. Scrolled a little too far. Okay, so I'm going to rearrange this equation to solve for theta. So we've got, let's see, negative 110 cosine of theta times 12 is going to equal negative 3002 minus 4,000 is going to be negative 1,002. Let me just double check that. Yeah, I thought I was a little wrong on that. Oh, I'm sorry. I don't know where I got that 2 from, actually. I forgot that we rounded, and we're just using that it's at 4,000 meters. So this is actually going to be just 3,000. Okay, so 3,000 minus 4,000 is going to be negative 1,000. Both of these negative signs are going to cancel, and then we can divide 1,000 by 110 times 12 to get rid of this 110 and this 12. So then we leave that cosine of theta equals 1,000 divided by 110 times 12. You could calculate that out if you want, but I like to leave all my calculations for the very end. So to solve for theta, we have theta equals cosine inverse of 1,000 over 110 times 12. And if you plug that into the calculator, 1,000 divided by 110 divided by 12 is equal to 0.75. And then you take the inverse cosine of that to get an angle of about 40.75 degrees. So that's our launch angle. So we now have everything we need to solve our y equation. So this is going to be y of 12 equals 3255 plus 110 sine of our new angle, which is 40.75 degrees, times 12, minus 1/2 times negative 9.8, which is our acceleration due to gravity. Actually, I'm sorry, this is going to be positive 9.8 because I put the negative sign right there instead. And then times 12 squared. I'm just going to go ahead and plug this into the calculator on my own, but I urge you to do the same, and you'll get an answer of about 3,408.77 meters as our y distance. So that gives us the vertical position in meters of the flare at time t equals 12 seconds. We have our ideal launch angle, and we have solved this problem. All right, for this last problem, we have that Stonewatch has identified the location at Olympus Station. We have their GPS coordinates in X and Y, and they're gonna deploy a UAV to deliver supplies to them. It has an altitude of 300 meters above Olympus Station. It cruises with an airspeed of 25 meters per second. And then it wants us to draw a diagram, write down what we know and what we need to find, calculate fall time, and do a few other things. So I'm first gonna draw our same diagram. We have Olympus, and then we have Stonewatch. Again, this is 0, 1850, and then this is now 4125, 3375, based on this here. And then there's a drone up here. It's moving at 25 meters per second. And then it's going to drop a package that's gonna land at Olympus here. We know that the distance in Y to the drone is 300 meters based on this information. And we need to know the X coordinate here for the distance, basically the point that it drops, so that it'll hit Olympus. So what we know is we know Stonewatch's location, we know Olympus's location, we know the drone's Y location, and we know the velocity of the drone. What we need is the time for the package to hit the ground and the release distance, delta x. So, first thing I'm going to do is I'm going to solve for the time. I'm going to come down here actually. I'm going to use y of t equals 3675. This comes from the dy here. And this just comes from the fact that it is 300 meters above this 3375. So this is our y naught. And then there's no velocity in the y direction, at least no initial velocity. So the package will be released essentially from rest in the y direction from the drone. So the thing acting on it is going to be minus 1/2 g t squared. And then we can rearrange this because we know that the final y, where it's going to end up, has a value 3375. So 3375 minus 3675 is going to be negative 300 is equal to negative 1/2 gt squared. Divide both sides by negative 1/2. Sorry, 1/2. And we'll get that, well, I guess we would multiply both sides by -2, actually. So we get that 600 equals gt squared. Divide both sides by g. So we get 600 over g equals t squared. Take the square root of both sides, and we get the t equals the square root of 600 over g, which is 9.8 meters per second. If you plug that into the calculator, you'll get that it's about 7.82 seconds of time. So now we need to plug that into our x of t equation. So x of t is going to be, I'm going to say that the x naught is what we're looking for here. So this is our delta x. I'm going to call it x naught. So the initial x position. And then plus 25, this is v naught. Because the package is in the plane, it's going to be traveling at the same initial velocity as the plane. And this is multiplied by time, which we found to be 7.82 seconds. And then this x of t is the final x position of the package, which is at 4125. So our full equation is 4125 equals x naught plus 25 times 7.82. So I'm going to go ahead and rearrange this and do 4125 minus 25 times 7.82 will equal our x naught. And if you plug this into the calculator, it is, let me do it real quick, 4125 minus 25 times 7.82 is about 3,929.5 meters. So that is the that's the distance from Olympus that the drone will have to release the package from. So to determine the offset, we just do 4125 minus 3,929.5, which is, plug it in, 4125 minus 3929.5, 195.5 meters. So basically, when the drone is 195 meters away from Olympus in the x direction, it needs to release the package. And that is it for this problem and it for this video.